Okay, I have taken the attendance. Only 32 students are present. So up to now, we have found this. Have defined random experiment. Sorry, the set of sample space S, sample space A set of all outcomes, and the probability. I found the probability for different events. So now chapter 3, 3.1 and 3.2, random variables and probability distribution of discrete random variables. Actually, random variables are two types: discrete and continuous random variables. So chapter 3 is devoted to the this discrete random variable, and chapter 4 will be for continuous random variable. Okay. So actually, random variable is needed because for large number of outcomes, if there is large number of outcomes, so it is very difficult to list all the outcomes and then find the probability for some events. Okay. Also, random variables will help the experiment to think differently. Okay, using mathematical concept, that's mathematically you can think differently using random variable. So the concept of random variable allow us to pass from the experiment outcomes themselves to numerical function of the outcomes. That is, we assign using random variable for each outcome to a real number, any real number, set of real numbers. You know the set of real numbers, right? So we assign for each outcome a real number. And the quantity that we observe in an experiment will be denoted by capital X, and it is called random variable or stochastic variable. And mathematically, what is random variable? Mathematically, it is a function. It is a function from the sample space to the set of real numbers. Okay, here S, capital S, the set of all outcomes, that is sample space. R is the set of real numbers. So the random variable X is a function from this set of all outcomes to the real numbers. That is, domain here is a set of all outcomes, sample space, and codomain or range is a set of real numbers R. That is, for each outcome S, each outcome of the sample space S, we assign a real number. Okay. That is the concept of this random variable. For example, see this. Consider an experiment in which 9-volt batteries are tested until the one with acceptable voltage. And acceptable voltage means success. Suppose we get the acceptable voltage, means this means that is success. So and it is generated by S for acceptable voltage. And the sample space then is S, comma f of S, f f s, and triple f s like this. And define random variable X, which counts the number of batteries before the experiment terminates. Okay. Then what will be the values, possible values of X? So we consider an experiment in which 9-volt batteries are tested until one with an acceptable voltage. So we are testing this batteries, and if we got the acceptable voltage, then we stop the experiment. Okay. Not got, then we continue the experiment. So for this, the outcomes like this. Suppose in the first attempt or first trial, we get the acceptable voltage, then this is success, means S only. In first trial, you get the success, that is acceptable voltage. Okay. Second possibility may be, suppose we did not get in the first trial, that is second trial we got success. That means we got acceptable voltage. Then the outcome is Fs. Okay. And another possibility is f of s, that is first two times we failed, but in third time we got the acceptable voltage. So third possibility is f f s. So in this way, the possible outcome is as fs, double fs, triple fs like this, and fourth fs like this. Okay. Now we define a random variable x which counts the number of batteries before the experiment terminates. Okay, and x counts the number of battery. So you see this, the random variable x is a function from s to r. That is, for each outcome we assign a real number. So here outcome, first outcome is S. So what is the S? X means here X count the number of batteries we tested here. So for the first outcome is we have tested only one battery, that is okay. So here X equals to 1. That is the real number 1 we assign for this outcome is the real number 1. So X equals to 1 for this first outcome. Similarly for second outcome Fs, okay, here we tested two batteries, so X Fs equals to 2, because here we count the number of batteries before the experiment terminates. Similarly, x ffs equals to 3 in this way. So possible values of x will be then 1, comma 2, comma 3, comma like this 4, okay, 5, comma 6, comma 7 like this. So this is an example of random experiment and define on random variable.
So,
Now, yes,
so can you explain this once more? So,
this example,
yes, sir.
yes, yes. So for this example, suppose we take an experiment in which 9-volt batteries are tested. Okay, until on with an acceptable voltage. So we continue the experiment until we got the acceptable voltage. So if we got the acceptable voltage, then we stop this experiment. Okay, there are so many batteries, no problem. There are so many infinite number of batteries, no problem. Just we check the batteries. If uh, we got an acceptable voltage, then we stop this experiment. Okay, suppose we take one battery, okay, and tested, and the first attempt if we get the acceptable voltage, then means we have got success, that is we got the acceptable voltage. So one possibility here is s, the first outcome, see in this s. Okay, and suppose we did not got in the first attempt the acceptable voltage, in second attempt we got the acceptable voltage, so for this the outcome is fs. Okay, similarly ffs, triple fs. Okay, is it clear this how it set of all outcomes are coming here?
Yes, sir.
Yes. And now we define on random variable x, capital X, which counts the number of batteries before the experiment terminates. Here x counts the number of batteries before the experiment terminates. Okay. Suppose for the first outcome, if we get the acceptable voltage means experiment terminate. So before this, how many up to this how many battery we have tested? That is x number of batteries here count. So here x is, for first outcome is we have tested only one battery, so x equals to 1. Similarly, for the second outcome Fs, we have tested two batteries, Fs equals to x, Fs equals to 2. Okay, and x ffs equals to 3. Similarly, we have tested three batteries like this. So in this way, x can take the value 1, 2, 3, 4, 5, 6, 7. So this you can see this x are taking the value that is the real numbers. So that's why x is a function from the sample space to R. For each outcome of the sample space, we assign a real number here. Okay. Okay. See another example. A simple example, that is tossing a two coins. Suppose a random experiment, tossing, in the tossing of two coins, tossing of two coins. Okay. So what are the set sample space here? What are the outcomes for this experiment? Yes. How many outcomes are there in the tossing of two coins?
Sir, 4.
Four outcomes. So what are the outcomes?
Four.
So head
Yes.
tail head and tail.
Head, head, tail, or tail head. So these are the possibilities for this experiment, random experiment. Now, if you define this random experiment X, okay, random experiment is X as the number of heads. Suppose we count the number of heads. X counts this number of heads. Okay. Actually, you have to define this random variable according to your problem. That is what you have to find. That is, you can answer this question in the last line of this question. That is what you have to find. Suppose you have to count the number of heads or number of tails, then you can define X as number of tails or number of heads. Or you have to count the number of cars like this, then you can define X as number of cars. Okay, for the particular problem. So suppose for one questions we defined here X is equal to number of heads, that is random variable. Okay, and we have seen that X maps S to R. Okay, that is S means here the sample space. So element of a sample space here is head, tail, head, tail, and tail head. So for the first head, what is the value of X here? Can you say? X counts the number of heads. How many heads are there in this outcome? A head.
Two heads.
So X value is 2 here. Similarly, X tail
Sir,
tail.
head.
Okay, X tail tail. How many heads are there here
Zero.
for this outcome? 0. No head, so 0. Similarly, X tail head, one head only there, so 1. X head tail, that is one head only there, so this is 1. Okay. So these are the possible values of the random variable X 0, 1, 2. Okay, that is possible values of X. Then X, consider it 0, 1, comma 2. This is X can takes only this value 0, 1, 2 for this random experiment.
So is it compulsory to write like x h h is equals to 2? Can we directly write x is equals to means the number of probability is equals to 3?
Now you can X H in you can write directly this X is 0, 1, comma 2.
Okay, sir.
Yes, 0, 1. The possible values of X. What are the possible values of the random variable X? Yeah, 0, 1, 2. Number of heads maybe 0 or 1 or 2, maximum 2. Okay. Then there is a term probability distribution. The probability distribution means then you have to find the probability for this values X. Suppose X is equal to 0, then what is the probability? And probability at X is equal to 0, at X is equal to 1, at X is equal to 2. What is the probability? Okay, this is the distribution that what is the probability that X is equal to 0? It's no head. Or what is the probability that X is equal to 1? Or this type of probability, you have to find X less than equals to 1. That is at most 1 head, at most 2 head. Okay, like this. So this is the example of random variables. Now random variables may be two types: a discrete or continuous random variable. Okay. Now there are two types of random variable, that is discrete random variable and continuous random variable. So what is discrete random variable? You can get an idea that discrete means there is a discrete value should be there in the a discrete value should take the random variable X. Okay. So if the possible values of the random variable X, okay, is a finite set. or countably infinite set, then we say that this random variable is discrete random variable. Okay. That is, if we list the set of all possible values of random variable x, it should be finite set, either finite set or it should be countably infinite set. Then we say that this random variable is discrete random variable. Countably infinite set means you can count the element of that set. Okay, that you can count like a first element, second element, third element, like this. So I think all of you know this countably infinite set, uncountable infinite set. Can you give an example of countable infinite set? That is that countable. The set is infinite, but it's countable. You can count the element of that set. An example of countable infinite set. Anyone?
So might be total of the two dices when they are rolled.
No, if you take the two dices, means the number your possible values, that is the sample space, is the finite sample space. Okay, so x would be here the possible values of x is finite set. I'm talking about countably infinite set. Set is infinite, but it is countable.
even
You can
even
get
less
any.
than 50.
Huh? I'm not talking about any probability question here. Just set theory. That is, give an example of a set which is countable and infinite, countably infinite set. Countable infinite set means the set is infinite, but we can count the elements of that set. Okay, uncountable infinite set means the set is infinite, but we cannot count. There are so many elements in that set. Okay. So give an example of these two type of set: countable infinite set and uncountable infinite set. Okay, tell me the example of uncountable infinite set.
Stars in the sky.
But
Also
Yes,
stars in the sky.
yes, here it is infinite. Okay.
set of real numbers.
Yes, set of real numbers. If you take the example of set of real numbers here, so set of real numbers, so for minus infinity to infinity, there are so many elements in this set. Okay. So this is the one example of uncountable infinite set. We cannot count. And countable infinite set from the set theory. Can you give an example of set which is countably infinite?
Sir, set of natural numbers.
Yes, exactly. Set of natural numbers. If you take the example of set of natural numbers, the elements are 1, 2, 3, 4, 5, like this.
So set
There
of
are infinite,
even numbers.
even numbers also, yes. So there are infinite number of elements, but we can count. Like one first element is one, second, two, third, three, like this. So these are the example of countably infinite set. So you should know this countably infinite set. Okay. So if your possible value of random variable x, either a finite set or countably infinite set, then we say that it is discrete random variable. Okay. And for example, if we count the number of cars on a road, okay, or number of defective screws in a production, okay. So these are the example of discrete random variable. Okay. That is for an experiment, random experiment. If we count something, that means the random variable is discrete random variable, and distribution should be the discrete distribution. Okay. Similarly, continuous random variable. So continuous random variable means the possible values of the random variable x lies inside an interval. in the interval. Interval mean real interval means there are so many elements in that interval. Okay, that you can say uncountable infinite. Okay, so if the set of all possible values of the random variable x lies in a single interval or in the union of the interval like 9 to 10 or 20 to 30 or 0 to 1, 1 comma 2 like this. Okay. For example, suppose x is a random variable for a random experiment. Okay, so if x lies between 0 comma 1, suppose open interval 0 comma 1. So in open interval 0 comma 1, there are so many elements. There are infinite number of elements in open interval 0 comma 1. So this is not a finite set, of course, and we cannot count also the elements of this. So this is a continuous random variable because the possible values of x lies inside an interval. Okay, and for continuous random variable, for a particular value of the random variable x, the probability is always 0. For any possible value of the random variable x, suppose c, then probability of x equals to c will be 0 for continuous random variable. For example of this continuous random variable is electric voltage or rainfall or height. Or temperature, measure of temperature in a particular day. Suppose the temperature lies between 30 to 35. So the temperature may be any value in between 30 to 35. There are so many values in 30 to 35. That is an example of this continuous random variable. So now see one example and tell me that this random variable is a continuous or discrete. So this is the question number 7 of 3.1. For each random variable defined here, describe the set of possible values for the variable and state whether the variable is discrete or continuous. The first one is here. The first one is x is equals to the number of unbroken eggs in a randomly chosen standard egg cartoon.
The
In this
continuous.
question, huh? Is it discrete or continuous? This random variable x.
Continuous.
Why continuous it is?
So because the set will be in the between the interval, now the carton that contains.
No, no.
Sir, this is
If you
a
count,
discrete, sir.
Discrete, sir.
yes, discrete random variable. Okay, because we are here we count. If you count something, that means that the random variable is discrete always. Okay, if you count something, count means here counting now 1, 2, like 3 to 4 like this. Okay, so if you count something, that means this random variable is discrete random variable. Okay, otherwise this is the number. If we count here the number of unbroken eggs in a randomly chosen standard egg cartoon. Okay, suppose that in a standard egg cartoon contains 12 eggs. Okay, then what are the possible values of x? Suppose that the number of egg, an egg cartoon contain
Finite.
12 eggs. Okay, so what are the possible values of x then?
1, 2, 3. 0, 1, 2, 3, 4. Up to
Up,
12.
up to 12 exactly. Okay, then the value of x will be 0, 1, 2, 3 up to 12 because here x counts the number of unbroken eggs and total eggs is 12. So it may be that no unbroken eggs means x is equal to 0. One unbroken egg, that is x equals to 1. Two unbroken egg, x is equal to 2 like this. The possible values of x is here 0, 1, 2, 3 up to 12. So this set is finite set. Is clear? 0 up to 12, only 13 elements are there. So this is finite set. Finite set means this random variable x is discrete random variable. Okay. If the set is finite, then always it is discrete random variable. And y, suppose y, the random variable y defined as the number of students in a class list for a particular course who are absent on
Discrete
the first day of classes. Yes,
or discrete.
it is discrete. What are the possible values of y?
So if we assume that a class has 50 students, then maximum 7 to if 7 to 8 people are absent, so we can count it. No?
Yes. You can count. It is yes. You are right. That is the discrete random variable. Oh, okay. Suppose there are n students. Suppose n is any natural number. Okay, finite number n here. Suppose there are n students. So what are the possible values of y? Y can takes. Can you see?
0 to n.
0 to n exactly. So if there are n students, so then the possible values of y will be 0, 1, 2, 3 up to n. 0 means no absent. Okay, 1 means 1 absent, 2 absent, like this. So possible values of y 0, 1 to n. So this is the example of, you can see here, countably infinite set. This is the sorry, this is finite set. Sorry, so this is finite set. Finite set means this is discrete random variable. Okay, 0, 1, 2 up to n. This is discrete random variables. Okay, see the deep, the length of a randomly selected rattlesnake. The length. Actually, if you count something, that means the random variable is discrete. Okay, and if you measure something, that means that is the continuous random variable. Okay.
So
So
why?
here x,
Because the length cannot be infinite; it can be finite, no?
yes, it is finite.
So sir, why it is not discrete rather than that of the continuous?
Okay, it is given. It is, you have to seek for this. The x is defined as the length of a randomly selected rattlesnake. So there is only one snake we have. Okay, so we measure this length. Measure the length of the rattlesnake. So then, what is the values this x can take? Uh, can you say length? We measure here length of a rattlesnake. There is only one snake. We measure here length. Okay. So if so length can be negative. It can be
Okay.
negative length.
No, sir.
No, no. Okay. Also, it is a snake. So length cannot be 0 also.
Yes, sir.
So x should be greater than 0.
So we can maybe check the average length of a rattlesnake. Maybe I.
Yes. So x should be greater than 0. Then greater than 0, x can take any value.
But it can't be finite, no?
It can't be infinite.
It
X can
should
take
be.
any value. And greater than 0, any value. So if you suppose maximum, it can be 12. Okay, so 0 to 12, like, it can take any value in between 0 to 12. So actually the length lies in an interval here. Okay.
So
So
then
this is what,
n can be any value, no? If we
yes,
consider n is equals to 35.
So, but what can be the maximum value? We
it
don't
is
know that.
actually you have taken less than infinity, that is yes, less than infinity, finite length.
No, sir, I'm not asking that, sir.
Yes,
So you told now that x is greater than 0 and in between that of the n.
yes,
So if you take a means the value of n is equals to means approximately 25 feet, then rattlesnake cannot be means that big as anaconda. So yeah, the length should be fixed, no? 0 to 8, 0 to 12, so 4 of the rattlesnake.
No, no, the length is not fixed here. It may be any value, na? Length greater than 0, any value.
So that means I'm clear that the length can be any value.
Yes.
So the means since you have told x is greater
It,
than 0,
it is
so I'm
actually it will be finite, but it can take any value. It should be
okay.
finite length, but it may be it can take any values. So any values greater than 0 up to finite means there are so many values, so many real numbers is there. Okay. So this is the x lies here inside an interval. This is the continuous random variable. Okay. Suppose Lx here length of the snake, then Lx can be inside this interval 0 to infinity, greater than 0, less than infinity. And of course, this is not a finite set. There are so many real numbers in this between 0 to infinity. So this is
But in the first question, like we assume that the standard box of eggs the box contains 12 eggs. So,
yes.
so like that way, we can we not generalize a number like a random rattlesnake can only be 20 meters or 10 meters long. There should be a limit. No.
And it is not given actually the limit here. Okay.
Okay, sir.
Yes, sir. As we have means considered x is greater than 0, then
Yes.
if we take n
So,
as the finite
so
number, then
if
it will
there,
not.
so
The
if
length can be
there,
any from 0 to infinity any value. It can be. It is not mentioned. Yes.
okay.
Okay,
It is the
so
exact. Yes. But if it is given like this, that there are 20 snake and the 20 snake length is this like 10.5, okay, or 10.6 or 12. Suppose the data set given for 20 data set given of a length for 20 snake, then that is the discrete case. That is
so can't
different.
we write the set of all x? So can't we write the set of all x which belong to 0 to means greater than 0 and less than n, and fix the value of n, and n should be less than or this value or that value.
Yeah, yeah,
Yes, sir. Here you
yeah.
have written the set of all x such that Alex is greater than 0 and less than finite
In,
value.
I can write, no problem.
Okay, sir.
Yes. Okay, see this F, the pH of a randomly chosen soil sample. Okay.
Continuous.
Yes.
Sir, discrete na.
No, it is continuous.
Continuous.
Yes.
So what PS should be from the 0 to 14. So the chosen solve.
Yeah, exactly. From 0 to 14, so we can this maybe any value between 0 to 14. Okay. So any value in between 0 to 14 means there are so many values in 0 to 14. So this is continuous random variable. Okay. Yeah, 0 to 14. So in between 0 to 14, there are so many values. So
Sir,
here
can you
y is
explain
continuous
once more the
description,
continuous?
continuous random variable. Hmm?
Excuse me, sir. So can you explain once more the
Yes.
difference between the discrete and continuous? Sir, I'm little bit confused, sir.
Yes. So here discrete random variable means and the first thing, if we count something, then you can confirm that this is discrete random variable. Okay. And if you measure something that is like length here, okay, so then it is continuous random variable. Otherwise, if you can you can differentiate this by seeing the set of possible values of the random variable x. Okay. Suppose we have found the x, the possible values of the random variable x. If it is a finite set or countably infinite set, that is, you can count the element of that set, then it is discrete random variable, right? But if the possible values of x lies inside an interval, inside an interval like this, then it is continuous random variable. Is it clear? That is uncountable infinite set for this continuous random variable. For example, if your x lies between 0 to 2, so there are so many real numbers in between 0 to 2. So many real numbers, rational number, irrational number, so many numbers are there in between 0 to 2. Okay, so this is the case of continuous random variable. So if your possible values of x is an finite set or countable infinite set, like set of natural numbers, okay, then this is the case of discrete random variable. And if your possible values of x lies inside an interval, one is real interval like 0, 1, 1, 2, okay, then it is continuous random variable.
Okay, sir.
Yes. Next we see what is probability function or probability mass function. So we have seen that the random variable are two types, continuous and discrete. So random variable in short form we write r dot v, okay, and random variables are two types, the discrete random variable and continuous random variable. Now for both the cases, that is for discrete random variable and as well as for continuous random variable, we will see what is probability function and what is cumulative distribution function. Now to find this cumulative distribution function from the probability function, and we study some special type of discrete and discrete distributions, okay, and continuous distribution. For any probability distribution, if it is for the discrete random variable, it is called discrete distribution. And for continuous random variable, the corresponding probability distribution is called continuous distribution. So what is probability function or probability mass function also called it is for discrete random variable. The probability mass function, or in short form we write PMF. Okay, sometimes it is called simply probability function for discrete random variable. Okay. So the PMF that is the probability function or probability mass function tell you how probability will distributed uh, with respect to the possible values of random variable. This is so the PMF of the discrete random variable is defined as variable x is defined by px equals to we denote this probability mass function by small px. Okay, this is probability function or probability mass function is small px, and it is defined by, that is, we have to find the probability for each possible values of the random variable x, that is probability of capital X equals to x. This is the probability mass function. Small px equals to capital P, that is probability at capital X equals to small x. So here capital X is the random variable for the particular random experiment, and small x is the possible values of the random variable. Okay. For example, for tossing a two coins, we get this possible value 0, 1, and 2. So here probability mass function means px means we have to find the probability at x is equal to 0. Okay, then probability at x equals to 1, and then probability at x equals to 2. Possible values of x for tossing a 2 coins is this 0, 1, 2, and if x counts the number of heads here, okay, then possible values of x is 0, 1, 2. Then the probability is probability at x equals to 0, probability at x equals to 1, and probability at x equals to 2. So this distribution is called probability function. This is probability function or probability mass function. So probability mass function means we have to find the probability at each possible values of the random variable capital X. But for this function Px should be satisfy the following two conditions. Then we say that this is the probability mass function. That is for any PMF the following two conditions must be satisfied. The first condition is Px should be the probability mass function Px should be greater than equals to 0 for all x. Okay, and two, the sum of Px is equals to 1 over x. That is total probability equals to 1. Okay.
Sir, I couldn't understand what is PMF.
PMF at the probability mass function or probability function. This is for the discrete random variable. What is this? This is nothing but just probability. We have to find the probability at each possible values of the random variable x. So this is each possible values of random variable x. So capital X equals probability. Px means PMF. Px
So
means
probability mass function is a set of probabilities or a range of probabilities. Like,
you can say set of probabilities here.
okay, sir.
That is x equals to 0 and 1, 2. Okay, then Px equals to Px probability at x equals to 0 or probability at x equals to 1 or probability at x equals to 2.
Okay, sir.
So this whole thing, that is x equal to 0, 1, 2, this is the possible values of x, and then Px. This Px, then this is called the probability mass function. And for probability to be a probability mass function, it must satisfy the following two conditions. The first one is Px should be greater than equals to 0. That is, all the probabilities should be greater than equals to 0. It is obvious because Px equals to probability at x equals to capital X equals to small x here. And we know that probability of capital X equals to x, probability is always greater than equals to 0. Okay, and Px is equal to this means probability. Px means probability, so this should be greater than equals to 0 for all x. And summation of Px equals to 1 over x. So for each possible values of x, if we find the probability and if we add all the probabilities, this would be equals to 1. That is summation of Px over x equals to 1. For example, if we suppose the Px is given as this, Px equals to, suppose x equals to, at x equals to 1, at x equals to 2, at x equals to 3. So there are three possibilities. These are three possible values of the random variable x, and these three and possible values, the Px is probability is given as, suppose this is probability 0.1, and this is 0.3, and this is 0. Suppose 5. Okay, that is at x equals to possible values of random variable x. Suppose x equals to 1, 2, and 3, and probabilities are given as this. At x equals to 1, probability is 0.1. At x equals to 2, probability is 0.3. At x equals to 3, probability is 0.5. This is the so is it a probability mass function? Is it a probability mass function?
No, sir.
Yes. Because
It is
why it is not probability mass
because
function?
it is not a problem.
Because the
Oh,
summation is
summation
not
is
one.
not equal
Exactly.
to
The
1.
second, yes, yes, second property not satisfied here. Okay. That is summation of px here is equals to 0.9. That is not equals to 1. So this is not a PMF. Okay. Also, if any values, any probability is suppose p any function px is given with negative values, suppose px is equal to minus 0.3 at x equals to 2, then this is also not a probability mass function because the values of px is negative at some points.
Sir, what
Okay.
is the meaning of negative?
Suppose it is not given that it is a negative, it's not a probability function. It is not given. Suppose on function is given. Suppose, okay, just you have to check whether it is the probability mass function or not. If it is written that it is probability function, then no meaning of negative. Okay. Suppose any function, this is not probability function, may not be, no problem. Just suppose any function is given f of x like this minus 1 at x is equal to suppose 1, 0.5 at x equals to 2, and 0.9 at x is equal to 3. So any function it is. Okay. Now if we check for this, is it a PMF or not? See at x equals to 1, this take the function takes negative values. So this cannot be a probability mass function.
Okay, sir.
Okay, next class we will see what is CDF, cumulative distribution function, capital F of x, and how to find this probability function px from a particular random experiment. We will see, and how to find this probability distribution for this experiment, and we draw or we yes, we draw the picture of capital F of x and px small px, how it is distributed over this possible values of x. Okay, so I have already taken the attendance in the beginning of the classes. You can leave.
Thank you, sir.
Sir, I was not able to get my attendance marked.
Why? In the beginning, within 10 minutes, I have seen that only 30 students were present, 32 students. That's why I have taken the attendance. You should join the class within 5 minutes.
Sir, will take care of it from next time.
Okay, those who are present here, I'm telling you, you should join the classes within 5 minutes. Okay. If only 20, 30 students are present in the classes, if someone sick, my class that only 30 students present, total student is 70, above 70, and this is very bad. Okay, so you should join the classes and from the beginning. Okay, for today I will mark present, no problem. Okay,
Thank you, sir.
yes.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.